Video 18-5 buffers and hydrolysis of salts. So, buffers. Okay. A buffered solution is going to be a solution that you can resist changes in pHs if you add an acid or a base to it. Okay. Now, how do you make a buffer? Simple. Okay. You need to start out with a weak acid, and to it you have to add the anion of that weak acid. Okay. Or you can make it buffered as a base, and you have to use a weak base, and to it you have to add the cation of that weak base. Okay. And these basically have to come from salts. You cannot just simply add one of the ions, so the salt has to contain either that anion or that cation. Okay. Now, why does it work? Okay. Well, let's take a look at an acidic buffer. Okay. So we need our weak acid HA, and we also have to add a salt to it, and the salt has to have the same anion. Okay. And because you can't just add the anion, we'll use sodium as a cation. Okay. So what happens? You start out with the weak acid, okay, HA, and since it's a weak acid, it'll break up a little bit into H plus and A minus. Then we dump in the sodium salt with the anion in it. That fully breaks up into Na plus and A minus. Okay, the Na plus you don't worry about. It's not going to affect the buffer either way. But notice the A minus basically means that you now have lots of A minus in the solution. Okay, and these two concentrations, before you added the salt, H plus and A minus were equal to each other, right? Just like when we did the weak acid problems. But now they are not equal to each other. Okay, and basically you can consider this concentration to be the same as the concentration from the salt that you added to it. Okay, now, why is this buffered? Okay, if we add H plus to the solution, okay, what happens is the A minus that you have floating around there will react with it and neutralize the extra H plus. Remember, if you want to buffer a solution, you have to keep the H plus concentration and OH minus concentrations relatively constant. Okay, then that means your pH will stay relatively constant also. Okay, so what happens? This is the stuff that gets added. Because you have a lot of A minus in there, it turns into HA, and you just neutralize the extra H plus. Okay, now if you add OH minus, it reacts with the H plus that's in the solution. Okay, now that stuff will go away, but don't forget, this is basically acting like a reservoir of extra H plus. So it disrupts the equilibrium. Okay, and the HA says, hey, I lost some H plus, so let's go make more H plus, and you restore it. Okay, so here's a little graphic picture. Okay, here's our buffered solution. We have the weak acid molecule floating around. You get a little bit of H plus, okay, and there was a little bit of A minus in there also. But we also added more NaA, so that means we got a lot of A minus floating around there now. Okay, so what happens if we go and add some H plus to it? Okay. H plus is going to react with the A minus and neutralize it. Okay, so this H plus reacts with the A minus. Okay, this one went away. It's going to react with this one here and basically turn into more. The amount of H plus that we have in here stays constant. Okay, what happens if we add OH minus? And again, remember the idea is that the H plus amounts has to stay the same. Okay. Well, that'll react with the H plus that's floating around and neutralize the OH minus, okay, which is good. But now we lost some H plus, okay. But because this is an equilibrium between this, the H plus and the A minus, system says, oops, I lost some H plus, so AJ breaks up and replaces it. Okay, so basically this molecule right here breaks up, gives you an H and A minus, which you don't care about, but you do replace the H plus. So the concentration of the H pluses stays relatively the same. Okay, now, how do you find the pH of a solution that is buffered. Okay, so it's 0.1 molar acetic acid and 0.1 molar sodium acetate. Okay, so first of all, what's acetic acid? Okay, it's going to be HC2H3O2. Okay, it's going to break up, and this will be aqueous. It'll break up into H plus and acetate. Okay, and both of these are aqueous. Okay. Then, because it's an acid, we can write out a Ka equation for it. So that's going to equal the H plus concentration times C2H3O2 minus concentration, and divide by the concentration of the acid. Okay, it's like a weak acid problem, but it just got way easier. Okay, so we'll let X equal the concentration of the H plus since we're looking for the pH. Okay, now what is the acetate ion concentration going to be equal to? Okay, before we started, these two were equal to each other, H plus and acetate, but now we just added a whole bunch more of acetate to it. Okay, and sodium acetate, because it's soluble, all breaks up into Na plus and C2H3O2 minus. Okay, so since this concentration was 0.100 molar, it's a 1-to-1 mole ratio, the acetate will be 0.100 molar also. Okay, and just like in a common ion problem when we did solubilities, because you added a common ion, the concentration of that ion is pretty much going to be whatever you added. So this is just simply going to be 0.100 molar. Okay, don't worry about what was there initially from this, because when you do add it, it's going to shift to the left also. And don't worry about how much you lost. Okay, that makes this way easier. And also, what about this concentration of the acetic acid molecule? Okay, that used to be equal to the initial minus the amount that you lost, but it's going to shift back that way. So basically, all we need to make it equal to now in a buffered problem is just equal to the initial concentration, which is 0.100 molar. Okay, now this equation just got real easy. Ka is 1.79 times 10 to the negative fifth. Okay, and that's going to be equal to, that's X. This I do know. The acetate concentration is 0.100 molar. Okay, and then I'm going to divide by the concentration of the acetate molecule, or the acetic acid molecule, which is also 0.100 molar. Okay, and in this case, they happen to cancel out because the concentration of the salt and the acid were the same. Okay, so basically this means the H plus concentration is equal to 1.79 times 10 to the negative fifth, and then the pH will be the negative log of that, which will be, that'll be 4.747. Don't forget, 3 sig figs from that, so this has to have 3 decimal places. Okay. Now, last thing we look at, hydrolysis of salts. Okay, for a neutralization reaction, if you take HCl, which is a strong acid, sodium hydroxide, a strong base, you get water and sodium chloride. Okay, and the pH at the end point at 25 degrees will be 7.0. Okay, if we use a neutralization, we use the same base, sodium hydroxide, but we use acetic acid, a strong or a weak acid. Okay, the end point will be greater than 7. In other words, the solution will be basic. Okay, and it's not because you have extra sodium hydroxide. It's neutralized. Okay, moles of acetic acid, moles of sodium hydroxide are equal to each other. Okay, and this neutralization reaction, HCl, like what we used before in the top one, but now we use ammonium hydroxide, a weak base, okay, and exactly neutralize it. All the moles of acid, moles of base are equal. Solution will be acidic at the end point. Okay, now the question is why? In each case, all the acid and all the base exactly neutralize each other. Okay, well, must be the problem must be that the salt must be doing something. Okay, now a salt whose cations comes from a weak base will produce acidic solutions. Okay? And it doesn't matter if you started with an acid or base. As long as you have a salt where the cation is a weak base, you put it in the water, solution will be acidic. Okay? And if an anion comes from a weak acid, you put it in the water, it will produce a basic solution. Okay? Now, why? This is not the explanation. Okay? You have to show me chemically a reaction why it will be acidic or basic. So, the cation reacts with water. Okay? This is called a hydrolysis reaction, and it produces an acidic solution. Okay? So an example, this is the cation of our weak base, ammonium. It reacts with water, and it will donate an H plus to that, turn into NH3, and you produce hydronium ion. So now the solution is acidic. Okay? And if we take the anion from a weak acid, react it with water, it'll produce a weak base, or it will produce a basic solution. Okay? So here's the acetate solution, the acetate ion. This is the anion of acetic acid. Put it in the water donates an H plus to that, produces this molecule, which is not an acid, but you produce hydroxide in solution. Okay. Now, how come the Na plus and the Cl minus didn't react with water? Well, let's see. Is it possible that Na plus can react with H2O? Okay. And pretty much the water has to be able to either donate or accept an H plus. Okay. And since, that doesn't have an H plus, that's not possible. Okay. Can you donate an H plus over to sodium ion? Is this possible? No. Okay, so it's no reaction because Na plus cannot combine with an H plus. Okay, well, what about the Cl minus? Can that react with H2O? Okay, well, it can't donate an H plus because, again, there's no H plus there, so that's not possible. But it's possible that water could donate an H plus to the Cl minus, and you'd produce HCl, and when you lose an H plus from the H2O, you end up with OH minus. So you say, well, why isn't this now basic? This is a strong acid, which means it actually exists as H plus and Cl minus. And you still have the OH minus in there. Okay, so you get an H plus, but you get an OH minus. So it's neither acidic or basic. It basically just turns into H2O and Cl minus again, what you just started with. Okay, so there's no reaction that takes place. Okay, so the general rule. Okay, a strong with a weak produces whatever the strong substance was. So in other words, if it was a strong acid that combined with a weak base, okay, then basically what happens is the salt will be whatever the strong thing was. So it would be acidic. Okay? Or if we had a strong base that combined with a weak acid, because the base was strong, then the solution will be basic. Okay? And again, it's because of the salt that is being produced. Okay? And if it's a strong with a strong, then pretty much it's going to be neutral. Okay? Strong acid with a strong base, the salt that's produced will end up being neutral. Okay? Now, here's your review question. Which salt, when you put it in the water, will produce an acidic solution?